Let's go through this problem using the solution process steps. For this problem, we'll use the given system as a whole, which I've diagrammed up on the light board here. We've got our mass M1 on our frictionless surface. We've got our pulley, zero friction, stationary. We've got our cable. We've got our mass M2, our body M2, and we've got the surface down below it. I've also written up our target variables for this particular problem, which are the acceleration for each body, the tension force in the cable, and the time it takes M2 to drop to the surface below it. The only external forces in this particular problem are gravity. Everything else is included inside the system. Gravity acts on all bodies in the system, but that doesn't mean that gravity directly induces motion on each one of the bodies. So let's take a look at each individual body's response to gravity. We'll start with M1. M1 rests on a surface which supplies an opposing normal force counteracting gravity. There is no vertical motion for body M1. The cable is massless. That means the mass is zero. So the external force on the cable is zero. Force is equal to mass times acceleration. If you have zero mass, you have zero force. The pulley is fixed and does not move or rotate. There is zero friction between the cable and the pulley, so the cable slides over the circumference of the pulley. As we'll see in the future, if the pulley rotates, there are other issues that will concern us. So for now, the cable will just slide over the pulley. Our final body is mass M2, and this is suspended by the cable, and there can be vertical motion here. There's nothing to prevent this from moving. There are no other forces. There are no external forces here that are going to keep this from happening. So if an external force, gravity, acts on this, it's going to pull it towards the surface below it, which is actually the point of the problem. Let's trace the propagation of forces throughout the system due to gravity. So now we'll work our way through the diagram, labeling the forces that propagate through the system. As we label the forces, remember that we consider both the magnitude and the direction. For now, we'll only qualitatively consider direction in terms of is it going to move this way, is it going to move that way. Once all the forces are labeled and we see their direction, all of the different places that the forces are pointing, then we'll choose a coordinate system that makes the analysis easy. Based on that coordinate system that we assign, we'll add mathematical notation to these forces that allows us to quantify direction. So let's begin with mass M2, body M2. Gravity acts on M2 and creates a downward force. And we'll call this F sub g, and that F sub g is equal to mass M2 times gravity. M2 is connected to the cable, so M2 exerts a contact force on the cable, and we'll call that force F sub t for tension force. And that's downward. The tension force on the cable is downward. Due to Newton's third law, the cable exerts an equal and opposite force on M2, the difference being the direction of the force. So this means that we are also going to have a force on body M2 that points up, and the magnitude of that force is also Ft. The cable cannot stretch and is massless, so the entire contact force exerted by M2 on the cable is exerted on M1 by the cable. All this is doing is transferring that force up to this point here. F sub t is exerted on M1 in this direction. For the sake of completeness, Newton's third law applies again, and M1 also exerts a force F sub t on the cable. We'll just put it in there, but this is actually F sub t on the cable. Note that the combination of the cable and the pulley only changes the direction of the force applied to M1. That's all that's happening here. The force here is equal to the force here, it's just a different direction. When we consider the forces in play in this problem, they're all perpendicular in this direction and parallel in this direction to gravity. We'll choose an XY axis that corresponds to gravity. So let's use a slightly different color for this. We will choose a coordinate axis like this, where this is plus x, minus x, plus y, and minus y. Upward forces are positive y. Downward forces are negative y. Forces to the right are positive x. Forces to the left are negative x. So let's go back to the diagram and place negative signs that agree with our associated sign convention. We'll start down here with FG. FG is in a downward direction, so we will give that a negative sign. And we will also transfer that to the other side also. Ft exerted on mass M2 is in an upward direction, so this will be positive. Ft exerted by the mass by M2 on the cable is negative. The force is transferred up to M1. The force exerted on M1 by the cable is in the positive x direction, so this will remain as a positive value. And while we won't really need this force here, we can say that the force exerted on the cable by mass M1 is negative F sub t. Now we break down our system into individual bodies to calculate net force. We'll create free body diagrams for both M1 and M2. Let's start with M2. Gravity is down, tension is up. There were no other forces, so we'll assume, in fact, we'll draw this over here just to break it out. We have M sub 2, and we have force of gravity, F sub g going down, and there is a force F sub t pulling up. And we're going to assume this is going to be dropping down, that there's an acceleration in this direction. And that will be acceleration m2. So now we're going to draw a free body diagram for this, and we'll draw it on our coordinate axis. Maybe let's use a different color. So what we have here is Ft and F sub g in a different direction. Now, when we sum these forces together, there are no forces in the x and y direction acting on M2. So now we can come up with, we know that it's going to accelerate downwards, so this is going to be A2. We know that acceleration, force is equal to mass times acceleration, so this produces a net force that's equal to F sub n is going to be equal to M2 times A2. And we also know that this direction is downward, so we will assign a negative sign to each one of these. And now we can come up with an expression that describes the motion for this. And this will be F sub t minus F sub g is going to be equal to minus M2 A2. And let's just note this over on the side here. We will come up with M2, and our equation for motion for this particular body is going to be Ft minus Fg is equal to minus M2 A2. Before dealing with the tension force of the cable, it's important to recognize that weight and normal forces still act on M1, and that those forces have to be represented in the free body diagram. So let's just take a look at M1, and we know that there is some F sub g pulling downward, but we also know that there is some opposing force, N, that is opposite. This produces zero motion in the vertical direction. And we also know that from our diagram that we have F sub t pointing off to the right, as in the diagram over here. Now we're going to use this information to create a free body diagram and some forces in the same way that we did before. So once again, we will draw our coordinate axis. Let's make that a little darker. And we have to include the gravitational force and the normal force in this diagram. So what we'll have is the gravitational force down. We'll have the normal force up. And we also have our tension force off to the right. But what we notice is that the y direction forces cancel each other out, and all we're left with here is the tension force in the positive x direction. So from this, we know that we use Newton's law again. If there is some force, Ft, that's applied to a body M1, this is going to produce an acceleration where the mass M1 times the acceleration of that body is equal to the force. So we're going to write this down here also. Now that we have the equations of motion for our system, we're going to combine the individual body analysis that we've done. We have equations for M1 and M2, and we're going to combine them together to find our target values. So we need some way to relate the equations for M1 and M2 together. These two analyses are connected by their shared force. Ft appears in both of these equations. The important piece of information that we use to make the connection is that the cable connecting M1 and M2 does not stretch. This means that M1, M2, and the cable connecting them all move with the same displacement, velocity, and acceleration magnitudes. The direction is not the same, but the magnitudes are the same for each of these bodies. We initially defined acceleration values as being independent, but now we know that they're actually the same magnitudes. The A that's moving in this direction is equal to the A that's moving in this direction. So if we take our equations here that we have for M1 and M2, now we can substitute M1, or we can just substitute A for A1 and A2. So let's rewrite those. So we have Ft minus Fg is equal to minus M2A. But we also know that F sub g is equal to m2g. So we'll rewrite the whole thing. Ft minus m2g is equal to minus m2a. And we have our equation for m1, which is Ft is equal to m1a. Now we can just make this substitution into our top equation here. We have m1a minus m2g is equal to minus m2a. And we can rearrange this, and we get m1a plus m2a is equal to, we bring minus m2g to the other side, m2g, we factor out an a, and now we just divide by the sum of m1 and m2. And this is the acceleration for each of these bodies. It's the acceleration for the cable too that moves between them. All three bodies will move at the same, with the same displacement, the same speed, and the same acceleration. So we can just combine these two together, and we will write those answers down, and this becomes m2 divided by m1 plus m2g. To find the tension force in the cable, we already have an expression for tension force, which is Ft is equal to m1 times a, but we just calculated a based on mass and gravitational acceleration, and so we can just substitute that in. It is equal to m1 times m2 divided by m1 plus m2 times g. That's the tension force in the cable based on the mass. So let's see if we can't squeeze that in down here. We have m1 times m2 divided by m1 plus m2 times g. To find the time it takes for m2 to drop to the surface below it, we have to go back to our kinematics. And the equations for motion for constant acceleration and zero initial velocity in a downward direction, the velocity is going to be equal to minus the acceleration times the time that things have been moving, and the difference in displacement is going to be equal to minus 1/2 at squared. We just remember this from our study of kinematics earlier. So we do know that in this particular case that the distance, back from our original problem, between m2 and the surface, delta S is going to be equal to minus d. Remember, this drops in a negative direction. This drops in a downward direction, so we assign a minus sign to the d. So we're just going to replace this, substitute minus d into this equation, and solve for t. So we have minus d is equal to minus 1/2 at squared. And we change things around a bit. We move the 2 up to the top. 2d divided by a is equal to t squared, and our t will be equal to root 2d divided by a. Now we evaluate the original problem in terms of the equations that we have. Now we don't have any hard numbers that we've plugged into this particular problem. This has been a general solution. But what we can say is that in the absence of any sort of frictional forces or contact forces around the pulley, or any frictional forces along the surface between M1 and the surface below it, that there will always be motion that accompanies this. Gravity acts on M2 and pulls M1 along as it pulls M2 down. And that's our solution. We will take a next step and we will try this with multiple bodies that are affected by gravity instead of just one to see what happens. Stay tuned.